Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at problem solving with trig functions. Now, we looked at trig functions last year, sine and cos functions, so they model periodic data. Data whose quantities go up and down, up and down, up and down. An example of this, daylight in Canberra. So what actually happens, we'll look at a graph here. The daylight at January 1, middle of summer, there's a lot of daylight, so it's up here. Then the number of hours of daylight gets lower and lower until it reaches the low point at the winter solstice. For us in the southern hemisphere, that's around about June 22. And then it starts going up, and then next summer, December 31, the number of hours of daylight would be very high again. And then, that's the end of 1 year, and then the next year it goes up and down, up and down, up and down. So that's what trig functions are good for. And that's exactly how daylight in Canberra works. So this function here is a good model of that. It's not 100% accurate. By this model, January 1 would be the longest day, where it's actually December 22, but it gives us a rough indication. I can substitute in x, which is the number of months after January 1, into this equation, and it will give me a good indication of how many hours of daylight there will be. Okay, so the question is asking us how quickly the number of daylight hours is changing on September 1, 8 months after January 1. So because we're asked how quickly something is changing, we're talking about a rate of change, and straight away you should think calculus. We want to know how quickly this function is changing when x equals 8, because x is the number of months after January 1. So all I need to do is differentiate this function here and substitute x for 8. So I purposely chose something like this because it is quite a complicated looking function, but its derivative is actually pretty simple. So to differentiate this function, I'll do it down here. So we're going to leave the 2.34 alone to begin with. Now remember, we multiply by the derivative of what is in the brackets. So the derivative of this function in the brackets is just 0.5536, just the coefficient of x there. Nothing complicated about it. So then we change the sines and coses around. So sine, the derivative is cos. So we make that a cos. Remember, if this was a cos, the derivative is minus sine. If it was cos, we'd change it to a sine and put a minus out the front. But because it's sine, derivative of sine is positive cos x, we can just change it to a cos and no need to put a negative out the front. So remember, what was in the bracket stays there. It doesn't change. So it's still going to be 0.5536x plus pi on 2. Okay, that part won't change, and of course when you're differentiating, the constant vanishes. So just remember, when you're differentiating with trig functions, you must do everything in radians, because the derivative of sine x is cos x only when x is in radians. So that's why it's really important your calculator's in radians. So if I want to know how quickly it's changing on September 1, 8 months later, all I need to do is take my x and change it to 8. So I put all of that in my calculator and I get a number about 1.24. So what that means is, on September 1, the number of daylight hours is increasing by about 1.2 hours per month. Each month around that time, there is an additional 1.2 hours of daylight. Again, as I've said in all the other videos, I want us to understand this is an instantaneous rate of change. This is the rate 8 months after January 1. It's not an average rate. It's not the average rate of change between January and September. It's the rate of change at one instant in time. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.